Welcome to this special episode of Frequency Matters, the R from MicroWave Update series. I'm Pat Hindle, and I'm talking with Marcus Hasselblad, CTO at Gapwaves. Welcome, Marcus.
Hi, thank you, Pat. Nice to be here, and I really look forward to have this conversation with you.
Yeah, Gapwaves has a really unique waveguide technology that's used to make low-loss antennas. Can you tell us about that technology and how it works?
Yeah, sure I can. And as you say, our technology is really unique, and it really gives the opportunity to benefit from waveguide performance in a new way compared to in the past. And as you know, Pat, waveguide has always been there because of its high efficiency with respect to low losses. And there is, of course, no difference in the gap waveguide technology. We also benefit from the low losses in waveguides. But in addition to having this good performance, waveguide has always been cumbersome when it comes to manufacturing because you need this perfect contact between the walls and the top and the lid of the waveguide for it to perform. And this is what our technology actually has a solution to. So we are using a pin structure or a meta surface, as we call it, where we actually can remove the requirement of contact between the walls and the lid. And instead we introduce a row of pins to work as an artificial wall, if you would like to, or a surface which prohibits the wave to propagate. This results in that we can actually put together a waveguide without having perfect contact. And this enables a lot of opportunities when it comes to how to mix and match materials and how to produce such a waveguide. So in the end, we have now today waveguide performance available to a very attractive cost level and with good yield and high volumes, which is really what our technique is about.
Yeah, I'm always amazed at how well that works.
Yeah, I am as well. You know, the best one is when you put a kind of thin film between the wall and the lids, and you can really see that it works, and you know that there is no contact between the two elements. But it's, you know, to mention a few of the good upsides with this technology is that we get less stringent requirements on manufacturing. Because of not having to have perfect contact, we can relax some requirements on planarity when manufacturing our waveguide. We can also combine materials, as I said, and we do that at Gapwaves. You know, we do injection molded pieces, and we combine that with sheet metal. And that results in a more cost-efficient antenna solution, and it also builds less height than having to build it with, for example, 2 injection molded layers. In addition, we can also see that the fact that we don't have to solder or glue the lid together with the bottom plate gives an increased robustness for stress and mechanical wear out. So our solution is more rigid when it comes to thermal cycling and so on, which is really an important parameter, for example, in automotive applications.
Yeah, you mentioned automotive radar. That's a really good fit for this technology. You know, what advantages does Gapwaves bring to this market?
Yeah, there are a few things that really stands out. Of course, first of all, automotive radar is at 80 gigahertz. So it's a high frequency, and at the front end, you know, between the low noise amplifier or the power amplifier, if you so want, you don't want any losses at all. So of course you would like to have a waveguide antenna. At the same time, automotive industry is a very cost optimized industry. So you cannot really afford any bulky, costly, expensive solutions. So this is where our technology now fits really, really well into the radar applications. And just to give some, you know, examples or flavors of it, radars today in automotive industry starts from 6 to 8 channels, like 4 receivers and 4 transmitters. But there are also sensors that, you know, cover up to almost 100 channels. So thinking about 100 channels and an antenna system, you realize there is some routing that has to be done from the integrated circuit out to the actual position of the antenna. So having a waveguide solution there is a really must. In addition to the efficiency or the low loss, you also get some other functionality. When you actually use the waveguide or gap waveguides technology for the antenna, you can feed directly from the integrated circuit to the antenna. This is normally called launcher in package. And the effect of that is that you release the requirement from the printed circuit board to carry any high frequency signal. And Having done that, you can change the laminate and have a more cost-efficient laminate in the radar solution. So it actually brings down cost on the radar. And the third benefit is that the antenna is actually placed on top of the circuitry, or on the bottom if you would like to. So you can shrink the actual area of the radar. And all car manufacturers know how hard it is to get a corner radar into the bumper. But having this, you actually can reduce the size and make the integration much more smooth for the automotive vendors.
And you've partnered with some automotive radar companies. Can you tell us which collaborations you're working on and what products were realized?
Yeah, we have quite a lot of engagements in the automotive industry. I would say that we have more than 10 ongoing engagements. Not all are public, but a few of them are announced, and I can share a little bit of them here. I would like to start with the engagement we have with Hella. It started a little bit more than 2 years ago, and we started to develop an antenna for their 6th generation corner radar. This antenna has now been developed and is ready, and will very soon be launched into production, in serious production in high volumes. During this period, Hella also found our technology so interesting, so they have invested and actually own 10% of the company today. And we continue to develop also for their 7th generation, but I would like not to comment on any release or what kind of products that is for confidentiality agreements, so to say. Then, in addition to Hella, we have also last summer signed a contract with Bosch, which we made public, I think, in July last year. Here we are developing imaging type of radar antenna, or high resolution type of radar antenna. And actually in this collaboration, we are not only doing the design and offering our technology, we are also aiming to become a supplier to Bosch with the start of production around 2026. So this is a huge step for Gapwaves, moving into the value chain, not only providing technology, but actually also providing design technology together with supply of antennas. So those are the two publicly announced automotive tier ones we're working with. Then we have few other cooperations with, for example, Smart Micro and Under, two corporations we really cherish a lot, and we have been working with those two companies for a few years. And we are designing different variants for traffic management as well as autonomous vehicles together with them. And we do continuously produce small volumes of antennas to them, hoping that they will soon go up in numbers as well. Then, of course, we also have Veoneer. That was the first automotive tier one that signed an agreement with us. As we all know, they have been going a little bit back and forth the last years, but finally now, when they have teamed up with Magna, or Magna has teamed up with them, we really hope that and really see that it will come volumes out of our engagement with Veoneer in the near future as well.
And so what other uses does this technology have in other markets or applications?
Yeah, we have been trying our technology and done some different projects in the past in other segments. Primarily, it has been in the telecom segment, mobile phone systems, and the SATCOM. So there are still opportunities there, especially as frequencies go up a little bit higher than the, let's say, low 10-ish gigahertz that we have, 10 to 30 for the mobile phone system and SATCOM. So we are engaging in academia a lot today and preparing for next generations of these systems.
And how about future developments? What do you plan doing with the technology going forward?
Well, there are a few things. The industry always pushes the frequency higher, so we are really aiming to prepare our technology for, let's say, 100 plus gigahertz applications. Especially then for the 6th generation mobile phone system. Here we are working together with academia on different solutions to meet the needs there. We also see that there are discussions for the 130 to 150 gigahertz band for automotive radars a little bit. So one focus is, of course, to prepare that we can meet the needs for higher frequency. In parallel with that, we constantly try to improve our technology in terms of manufacturing cost in order to reduce the cost. So having said that, we actually have, during the last 1.5, 2 years, developed a new variant of our technology, still based on the fundamental principle of gap waveguide, but realized in a different way. We call this technology the mmWave, metal layer waveguide. So it's a pure metal structure. It has actually two advantages over the traditional injection molded waveguide, and it's very thin. You can make really large aperture, and it has actually a great potential to bring down cost even further. This technology will be shared more in detail at this year's European MicroWave Conference in Berlin now in September. So stay tuned to learn more about our new mmWave technology.
Well, great. Thank you, Marcus, for talking with me today about the Gapwaves' unique antenna technology and its applications. To our audience, you can find more videos at videos.microwavejournal.com. Thanks for watching.